Alright, let's dive into the first topic and explore how the uneven heating of the Earth's surface by the sun leads to the creation of wind. This might sound a bit complex at first, but don't worry, we'll break it down for you. So, why is the Earth's surface heated unevenly? Well, the Earth is a sphere, and the sun's rays hit different parts of the planet at different angles. This means that some areas receive more direct sunlight and heat than others. For example, the equator gets more direct sunlight than the poles, leading to warmer temperatures near the equator and colder temperatures near the poles. These temperature differences create what's called air masses with different densities. Warm air is lighter and less dense, so it tends to rise, while cold air is heavier and denser, so it sinks. This movement of air creates a circulation pattern, which ultimately drives the formation of wind. When warm air rises, it leaves an area of lower pressure at the Earth's surface. At the same time, the colder, denser air that's sinking creates an area of higher pressure. Air always moves from areas of high pressure to areas of low pressure, and this movement is what we experience as wind. In a nutshell, the uneven heating of the Earth's surface by the sun creates temperature differences, which then lead to differences in air pressure and ultimately result in the formation of wind. Cool, huh? Now that we've got a basic understanding of how temperature differences drive wind formation, let's move on to the next topic and investigate the role of atmospheric pressure in wind development. Now that we've explored the uneven heating of the Earth's surface, let's delve deeper into the role of atmospheric pressure in wind development. As we mentioned earlier, air moves from areas of high pressure to areas of low pressure, and this movement is what we experience as wind. But how exactly does this happen? Let's investigate. Atmospheric pressure is the force exerted by the weight of air particles in the atmosphere. As we know, warm air rises and leaves an area of lower pressure at the Earth's surface, while cold air sinks and creates an area of higher pressure. These pressure differences are the driving force behind the movement of air. When air moves from high pressure areas to low pressure areas, it creates a flow of air called wind. This process is a natural attempt to equalize the pressure difference between the two areas. Essentially, the wind is the atmosphere's way of redistributing heat and maintaining balance. So, how does this pressure difference affect the speed and direction of the wind? Well, the greater the pressure difference, the stronger the wind. Wind speed is directly proportional to the pressure gradient, which is the rate of change in pressure over a certain distance. In other words, stronger pressure differences lead to stronger winds. As for wind direction, it's determined by the orientation of the pressure gradient. Air moves from high to low pressure in a path that's perpendicular to the pressure gradient. This means that wind direction is influenced by the way pressure differences are arranged across the Earth's surface. In summary, atmospheric pressure plays a crucial role in wind development, as it drives air to move from high pressure areas to low pressure areas, creating wind. The speed and direction of the wind are determined by the pressure gradient, which is influenced by the distribution of pressure differences across the Earth's surface. With that in mind, let's move on to our next topic and learn about the Coriolis effect and how it influences wind direction. Moving on to our third topic, let's discuss the Coriolis effect and its impact on wind direction. You might be wondering, what does the Earth's rotation have to do with wind? Well, the Coriolis effect is actually a fascinating phenomenon that occurs due to the Earth's rotation, and it plays a significant role in shaping wind patterns. The Coriolis effect is a result of the Earth's rotation on its axis. As the Earth spins, different parts of its surface move at different speeds. For example, points near the equator have a faster rotational speed than points near the poles. This difference in speed causes objects, including air masses, to be deflected from their original path, as they move across the Earth's surface. Now, how does this deflection affect wind direction? When air moves from high pressure areas to low pressure areas, it doesn't travel in a straight line as you might expect. Instead, the Coriolis effect causes the air to curve as it moves. In the northern hemisphere, this deflection causes winds to curve to the right, while in the southern hemisphere, winds curve to the left. It's important to note that the Coriolis effect doesn't create wind by itself. Instead, it influences the direction of winds that are already in motion due to pressure differences. The effect is stronger at the poles and weaker at the equator, which means that wind patterns are more significantly influenced by the Coriolis effect at higher latitudes. To sum up, the Coriolis effect is a fascinating phenomenon caused by the Earth's rotation, which influences wind direction by causing winds to curve instead of moving in straight lines. This effect plays a crucial role in shaping global wind patterns, which we'll discuss in our next topic. So let's proceed and study the global wind patterns and how they result from the interactions between temperature, pressure, and the Coriolis effect. Now that we have a solid understanding of the factors that influence wind, let's take a closer look at global wind patterns. There are three primary wind belts that circle the Earth: trade winds, westerlies, and polar easterlies. These wind patterns result from the interactions between temperature, pressure, and the Coriolis effect, which we discussed in the previous topics. First, let's talk about trade winds. These are the prevailing wind patterns found between 30 degrees latitude and the equator in both hemispheres. Trade winds blow from the northeast in the northern hemisphere and from the southeast in the southern hemisphere. They're called trade winds because sailors historically relied on them to navigate and trade across the oceans. The trade winds are caused by the combination of the Earth's rotation, the Coriolis effect, and the circulation of air between the equator and 30 degrees latitude. Next, we have the westerlies, which are the prevailing winds found between 30 and 60 degrees latitude in both hemispheres. Westerlies blow from the southwest in the northern hemisphere and from the northwest in the southern hemisphere. These winds are responsible for the movement of weather systems across the mid-latitudes, and they play a significant role in the Earth's overall climate. The westerlies are also influenced by the Coriolis effect, as well as the circulation of air between 30 and 60 degrees latitude. Finally, let's discuss polar easterlies. These winds are found near the poles, between 60 and 90 degrees latitude in both hemispheres. Polar easterlies blow from the northeast in the northern hemisphere and from the southeast in the southern hemisphere. These winds are cold and dry, as they originate from the high-pressure areas near the poles. The polar easterlies are also shaped by the Coriolis effect, along with the circulation of air between 60 and 90 degrees latitude. In summary, global wind patterns, such as trade winds, westerlies, and polar easterlies, are the result of the interactions between temperature, pressure, and the Coriolis effect. These prevailing winds play a crucial role in shaping the Earth's climate and weather systems. Now that we've studied these large-scale wind systems, let's move on to our final topic and examine the relationship between local winds and larger-scale wind systems, as well as the influence of factors like topography and proximity to bodies of water on wind strength and direction. As we wrap up our exploration of the factors that cause wind, let's examine the relationship between local winds and larger-scale wind systems. In addition to the global wind patterns we've discussed, there are also local winds that are influenced by factors like topography and proximity to bodies of water. These local winds can interact with and modify the larger-scale wind systems, creating unique wind patterns in specific regions. Topography, or the shape and features of the Earth's surface, plays a significant role in shaping local wind patterns. For example, mountainous regions can experience unique wind patterns due to the way air flows over and around the terrain. One such wind pattern is called valley wind, which occurs when air in a valley is heated by the sun, rises upslope during the day, and then sinks back down into the valley at night as it cools. This creates a daily wind cycle that is specific to that particular region. Proximity to bodies of water also has a significant impact on local wind patterns. Large bodies of water, like oceans and large lakes, have a moderating effect on the temperature of the surrounding air. This is because water heats up and cools down more slowly than land, which creates temperature differences between the water and the adjacent landmass. These temperature differences can lead to the development of local winds known as sea breezes and land breezes. During the day, the land heats up more quickly than the water, causing the air above the land to rise and create an area of low pressure. The cooler air over the water then moves toward the land to replace the rising warm air, creating a sea breeze. At night, the process reverses as the land cools down more quickly than the water. The cooler air over the land sinks, creating an area of high pressure, and the warmer air over the water moves toward the land, forming a land breeze. In conclusion, local winds can be influenced by factors like topography and proximity to bodies of water, and they interact with larger scale wind systems to create unique wind patterns in specific regions. Understanding the relationship between local winds and larger scale wind systems is crucial for predicting and interpreting weather patterns and climate variations around the world. And there you have it. We've explored the origins of wind, from the uneven heating of the Earth's surface to the role of atmospheric pressure, the Coriolis effect, global wind patterns, and the relationship between local winds and larger scale wind systems. We hope you've enjoyed this journey into the fascinating world of wind. So don't forget to see how discuss the time too, and we can now add the absolute